Okay, so you can see the presentation, right?
Yes, ma'am.
Okay. Okay. Just try to keep this. Okay. So I'm Sauravi. So I'm a PMRF fellow from Indian Institute of Science. I'm doing PhD on soft condensed matter here. So this course is on electromagnetic theory, as you all know. So this is so as far as I've seen the syllabus, uh, it starts with the basics of electromagnetism, where we talk about electrostatics, we talk about vector analysis at the beginning, and then we gradually move forward to seeing how we can calculate fields and use the electromagnetic theory to in our in applications. So now before I proceed, I would like to know, all of you guys are from physics background?
Ma'am, not particularly physics, but from electronics background.
Okay, right, right. So you know the basics, right? So
Yeah.
I think it won't be much of a trouble. This is a very, the first class is a very preliminary class about vector analysis, mostly vector analysis, and how we move from rectangular coordinates to curvilinear coordinates. And then very fundamental and preliminary ways of finding fields. Okay. So to start with, today's class would second. Why is it? Okay. So it will mostly concentrate on the basic concepts like vector analysis concepts, the theorems, and how to go to curvilinear coordinates. And then we'll see some problem solving. And finally, if you have some doubts, we will try to clear them. Okay. So to start with, we know that in nature there are these four main kinds of forces, like the strong forces, the electromagnetic forces, the weak forces, and the gravitational forces. Now, why we are interested in particular about this electromagnetic forces and why is it essential is because most of the forces that we see in our day-to-day life is actually electromagnetic force. The strong forces holds the protons and the neutrons together, and they are strong, but they are very short range, so we don't generally see them. And then the weak forces account to certain kinds of radioactive decay, as you can see, and they're also short range and far, far weaker. Okay. And gravity is stronger, but then it needs huge mass, so it works in the ranges of huge celestial bodies. So as you can see here, this is just an estimation which shows that how electromagnetic forces can be stronger in our realms, right? So the electrical repulsion between two electrons is around 10 to the power 42 times larger than the gravitational attraction forces. So even though gravitational forces are quite long range, but in our so the forces that we see in our or we experience is mostly electromagnetic in nature. So that's why electromagnetic forces are essential to understand. And if we go back to history, we'll see that electricity and magnetism were initially separate concepts, and then it was finally brought together, right? So this is just a history which shows. So we now know that they are very much related and they're intertwined. And so now we no longer consider them as separate subjects. Rather, we take it as one subject, that is electromagnetism. Now, it's important to understand this concept of field here, that because it's an action at a distance, so we say that suppose if we have a charge, there is an electric field around it. So if there is a collection of charge, that would result in a certain kind of electric field that would be experienced by some test charge, right? And then so it means that there's an action at a distance. So we can, while we can consider it as a field, like one-to-one correspondence, like one force, one particle, one charge, and then another charge, and what's the effect. What we can further do is we can find the effective field that is present in a particular area, and see what's its effect. So it's mostly a field theory, right? And then if we have a charge which is moving, which is uh, so I'll just So if a charge is moving, and in particular if it has acceleration, then what happens is that results in a radiation which we call the electromagnetic radiation, right? So this is just the introduction to electromagnetic theory and electromagnetic radiation. Now, what we need to revise now is that basic concepts of vector analysis is very important in all aspects of mathematical physics, or if we do electrodynamics, or if we solve electromagnetic theory problems. In all of the cases, this is very fundamental math. So we all already, I hope you guys already know about this, the laws of vector algebra, addition, subtraction, multiplication. These are very general things. And then you know that if there's a vector, and if you want to find the unit vector in its in that direction, what we do, we divide it by its magnitude, because a vector is known by its magnitude and direction. Now, if you say that the direction is fixed in some particular direction, and we want to find the unit vector in that particular direction, then what we do is we divide by the magnitude of that particular vector, right? And then a vector, suppose if you have it in a 3-dimension, you can see that a vector is defined as by different components in the different directions, right? So you can write it as a1 I cap plus a2 j cap plus a3 k cap. So in that case, the magnitude will be given by a1 square plus a2 square plus a3 square root, right? So now if you have to find the unit vector in the direction of A, what will you do? You'll have some vector A, and then you have to divide each of the components by this magnitude, right? And now there can be different kinds of fields. I was talking about fields. So there can be different kinds of field, like the scalar field or a vector field. Now, what do you mean by a scalar field? A scalar field is a field which has no direction. It just has a value. So if each point in space corresponds to some scalar value, some number, then it's called a scalar field. Like you can have a temperature plot, okay, and temperature has no direction. So in that case, it would be a scalar field, right? And then you can also have a vector field. So if you have a vector field, in that case, it has a direction. So at each point, it has a magnitude and a direction. So if you have a velocity, so suppose if you have a fluid flow, and then at each point, you have some velocity vector, right? So it has a magnitude and a direction. So that is a vector field. So now, depending on the scalar, whether it's a scalar field or a vector field, you have ways of defining it. So I don't know whether you know about divergence and gradient and curl. So there are ways of defining, or defining fields. So depending on what kind of field they are, you can define them based on, these are based on differentiations, and you can use those derivatives to define your field characteristics. Now, this is very simple. The dot product of two vectors is given by A dot B, which is given by AB cos theta, where theta is the angle between A and B. And then one can also define a cross product, which is A cross B, which is given as AB sin theta n cap. So this is a vector, and you can say this is a scalar quantity, right? So this is a vector which has a direction perpendicular to the plane comprised of A and B vectors. And as you can see here, it's non-commutative. So B cross A is not equal to A cross B. Rather, it's equal to minus of A cross B. So these things are clear to all of you, right?
Yes, ma'am.
Okay. So now let us look at the vector differential operator. So this is a del operator that we have seen quite a number of times. Now this operator can be used to find the derivatives of fields. Now, as I just discussed, that if you have a scalar field, so in that case, it is just a number which is varying from point to point, right? Now, what you can do is you can do a gradient of a scalar field, right? And if you do that, this is what you get. So what is gradient? Gradient is this operator, del del x of I cap plus del del y j cap plus del del z k cap. Now, when you operate this operator on some scalar field, what you get is a vector, right? And this vector obviously, as it is a vector, it has a direction. And what is its direction denoting? So its direction denotes the direction of maximum change of phi. So the direction along which phi is having the maximum change, that is given by the gradient of phi. Okay. And the magnitude gives the change. So now if we want to find the component of del phi along some particular vector A, so what you do is del phi dot A. So it's some unit vector A. So what you then get is a directional derivative of phi, which tells you the rate of change of phi along some direction A. So this is how you define when you have a scalar field. But now if you have a vector field, right, so given as V, so what, or some vector quantity. So what you do is you can find the divergence of V, which is given by, so now you have, this is the same operator, but then you operate it on this vector. So what you get is a scalar quantity, right? So this is the divergence which shows. So now if you see that if you have a field line which starts from a point and ends at the same point, so if it is a solenoidal vector field, what would you get? You would get the divergence to be 0. So similarly, you can also define your you can describe your vector fields by the curl of the vector quantity. So what you do is given as curl of V. Okay, so it's a cross product. This is also a vector. So here you get a vector quantity. So now these are some of the identities. So you can prove each of these identities, and these are very standard ones. So what is essential is to remember some of these identities. Like this one is a very important identity, which would come in numerous derivations throughout the course. And these are certain identities also very useful, like this identity as well. So these identities, as you go through the course and as you do the derivations and you read the textbooks, you'll see that this comes up again and again. So some of these identities is important to remember. Okay. So now let's move to curvilinear coordinates. So this is very important. And as far as I've seen for this week, this was one of the important section to be covered. So this is that suppose if you have some rectangular coordinate system, you have some vector, you have defined it by the coordinates x, y, and z. Okay. So now you move to spherical coordinate, or you move to cylindrical coordinate, or some curvilinear coordinates, right? So curvilinear means now you don't have this rectangular system of axis. You have some axis which is like this, right? So it has some curvature. So now if you move to that coordinate, how will your vector change? So that's the question that we want to address. So to start with, suppose if you have some rectangular coordinate, okay, which is given as x, y, and z. Now, the x, y, and z can be expressed as functions of u1, u2, u3. So, if you want to correlate, suppose you think of spherical coordinate or a cylindrical coordinate, it would be simpler. So, in cylindrical coordinate, what we do, we say that x is equal to r cos theta, y equal to r sin theta, and z is equal to z, right? So that means you can write x in terms of r and theta. You can write y in terms of r and theta. And you can also write z in terms of r, theta, and z. So there it's independent of r and theta. So you can say it's not a function. So it's like the coefficient in front of r is 0, something like that, right? So in a way, your components along this, like along the rectangular coordinates, can be expressed in terms of u1, u2, u3. So in your case, if you consider cylindrical coordinates, your u1, u2, u3 will be r, phi, and z, right? So now if that is the case, then what we can do is we can do a change of frames, right? Change of the frame in which we are seeing the vector. So what we say is, suppose your r is given as x I cap plus y j cap plus z k cap, okay? And r can also be a function of u1, u2, u3, because all of this x, y, z can be a function of u1, u2, u3. So what you want to do now is you want to draw a tangent vector to u1 curve at P. Hello? Hello? Any questions? Okay. So now what we want to do is, so see, like before I go to that part, let me first talk about this. So now you're moving to a different frame, okay, which is defined by different axes. So what you do is you define surfaces. So one surface is defined as u1 equal to some constant value. Another surface is defined as u2 equal to some constant value. And then u3 equal to some constant value. So now these are your new coordinate surfaces, okay? And each pair of this surface intersect at the curve, which is called the coordinate curves or lines, right? So now what happens is, so this u1, u3 curve, u2 curve, and u1 curve are now your axes that you want to, uh, like based on which you want to find your coordinates. Okay. So what now what you want to do actually is, suppose if you have some vector, you want to see how your vector changes along this direction, how your vector changes along this direction, and how does your vector change along this direction, right? So for that, what you now do is you draw a tangent vector to the u1 curve. Okay, suppose this is your u1 curve, you draw a tangent vector to the u1 curve, okay, for which u2 and u3 are constant. So what you are doing is you are doing del r del u1. So this is in a way telling you how r is changing along u1, right? Similarly, you find for u2 and you find for u3. What you do is you divide by the magnitude to get the unit tangent vector in that direction, and that is given by E1, right? So now if you think this, what is this E1? This is, suppose this is your line along which you want to find your, like find how your vector is changing, okay? So you find del R del U1 and then you divide by the magnitude. So in a way, you're getting a unit vector along this direction at each point, right? So that is actually what? So now if you consider, if you just think of your cylindrical coordinate. So if you want to see how your function is changing radially, right? So you find del R, del R, like del capital R, maybe your R is your, or del A, suppose your vector is A. So del A, del R, okay, R is your radial component. And then you divide it by the magnitude. So what you get is actually R cap, right? So similarly, you can find phi cap, and similarly, you can find Z cap, right? So this E1, E2, and E3 are actually unit tangent vectors to the different curves, right? And if you think back about your about the different coordinate systems, these are actually the r cap, phi cap, theta cap for your spherical coordinates, or r cap, phi cap, z cap for your cylindrical coordinates, right? And this magnitude, it can be like all these magnitudes, del r del u1 magnitude, or magnitude of del r del u2, or magnitude of del r del u3, all of this are called the scale factors, right? These are how your vectors are scaling along this directions. So now if you have some, so this is how your changes are happening. So when the next examples will come, you'll see how this concept is in like useful in all kinds of coordinate systems. You don't have to remember how things change from spherical to cylindrical. You can use the same concept for any kind of coordinate changes. So now, so you have some r, which is some vector, which is function of u1, u2, u3. So now if you want to find the arc length is some length value dr. Okay, so now you can write it in terms of this partial derivative. So you can write it as del r del u1 du1 plus del r del u2 du2 plus del r del u3 du3, right? And using this definitions that we just understood, so you can replace it here, right? So in a way now, if you have orthogonal systems, each of these unit vectors will have a dot product of 0 because the angle between them would be about 90. And then this is your arc element or arc length in that case. So if you want to find the magnitude of this vector, what you can do is you can find h1 du1 whole square plus h2 du2 whole square plus h3 du3 whole square. So that gives you the magnitude. So in spherical coordinates, you have like in rectangular coordinate, you have something like dx square plus dy square plus dz square. Now, when you go to your maybe cylindrical coordinates, what will you get? You would get something like dr square plus phi square d rho d phi rho square. Sorry, I'm just confusing between terms. So it should be dr square plus r square d phi square plus dz square. So we'll see how we get to that. But it would have some form like this, right? And then, so now if you again think back, so what you got is that this is the tangents, right? This is the tangents that you were drawing. And these are your individual components along all of these directions. So now if you multiply all of them, you would get the volume element. So this is your volume element that you would be getting, right? So now suppose if you have some vector given by a equal to z I cap minus 2x j cap plus y k cap, okay? And you want to represent this in cylindrical coordinates. So how do you do that, right? So see, you can write x, y, and z in terms of rho, like rho is your, rho is equivalent to, rho is equivalent to r, okay? So the radial component, and phi is how your angle is changing in the xy plane, and z is the vertical component. So you can write it as rho cos phi I cap plus rho sin phi j cap plus z k cap. So what you now do you find how r changes along, like changes as a function of rho, as a function of phi, and as a function of z. So what you are doing is actually you are finding this values, right? So in this here again, your u1, u2, u3 in this case is rho, phi, and z. So you are finding these values. So what do you get? You get something like this, right? And then now you divide them by the magnitude of these values, right? Magnitude of these vectors. So what you get? You get something like this. Clear? So what is E1? E1 is actually equal to R or rho cap, right? E2 is equal to phi cap, and E3 is equivalent to Z cap, right? So now this tells you how this unit vectors along your new coordinate system depends on the old coordinate system, that is the rectangular coordinate system unit vectors, right? And then you can simultaneously solve them to write I cap and j cap in terms of this new unit vectors, right? So now for your case, you know this is your vector. Now you have to change from rectangular system to cylindrical coordinate system, right? So you know how z, x, and y depends on rho and phi, right? So you can replace x by rho cos phi, replace y by rho sin phi, and z remains z here, okay? And then I cap, j cap, and k cap can be replaced by these values, right? So if you do that, now if you look at this expression, you only have the unit vectors along your new coordinate systems, and you have vectors like, values like z, phi, and rho, right? There is no x, y, z here. So now if you solve it and simplify it, so you would get some component. So a rho, e phi, e rho. So e rho is the unit vector along rho, plus some a phi into e phi, and some az into ez. So this gives you the components in the cylindrical coordinates. So is it clear to you? Clear to all of you?
Yes, ma'am.
Yes.
Okay. So now suppose if you have your cylindrical coordinate system, okay? So whatever we just discussed. Now, in order to prove, so all curvilinear coordinate systems may not be orthogonal, right? But mostly the systems that we work with, like the cylindrical coordinate system or the spherical coordinate system or the rectangular coordinate system, they are orthogonal coordinate systems where the different planes are perpendicular to each other, right? So in that case, so if you want to prove that your cylindrical coordinate system is orthogonal, how do you do that? So what you do is you find this dot products, right? This is something we just did in the previous slide. So now if you do a dot product of all these terms, you would see that all of them are 0. So this shows that they have a 90-degree between them, and that shows that this is a cylindrical coordinate system is orthogonal. Okay. What's important to note here is that, see, here you are dividing by the magnitude, right? Del R, del rho, magnitude of that term. Here you are dividing by magnitude of del R, del phi. And here you are dividing by magnitude of del R, del Z, right? And this values, so here you know this value is 1, this value is rho, and this value is 1. So these values are actually the scale terms which we just saw, right? These are the scale factors, right? These magnitudes are the scale factors. So this is how you can evaluate the scale factors for different coordinate systems. This is how you're doing it for cylindrical. Same thing will happen for spherical coordinate system, right? And now if you just remember how you got to this, and if you use this scale factors, you can very easily go from one coordinate system to another. So in general, this is how the gradient, divergence, and curl for different vectors look like. Okay. This is the general definition for any orthogonal curvilinear coordinate system, right? So for any system, if you know H1, H2, and H3, and if you know what, so these are the unit vectors along that particular coordinates. So then you can express your gradient, divergence, and curl, right? So for cylindrical coordinates, we saw that H rho is 1, H phi is rho, and Hz is 1. Similarly, if you solve for spherical coordinate system, you'll see that HR is 1, H theta is R, and H phi is R sine theta, right? So if you replace those values here, you'll get the expressions for the for those corresponding coordinate systems. So for spherical coordinate system, it would look something like this, while for cylindrical coordinate system, this will look like this. It is just the replacement of the H1, H2, H3 terms in the formula. Okay. Now let us just discuss this basic concepts of electrostatics, where we know that this is the Coulomb's law, which gives us a force on a test charge Q. We know that it's given as 1 by 4 pi epsilon 0 Q, capital Q by R square into R cap, where capital Q is your test charge. And you're finding the field or the force on the test charge due to some point charge, small q, right? And the different distance between them is given by R vector. Okay. And these things are pretty simple. So now if if the positions of both of these charges are given, what you do is you find the separation vector between them, which is given as the difference between their position vectors, right? And if you have number of force, several number of point charges, what do? You find, so it follows the superposition principle. So you can add all of these forces. Okay, so that gives you the net force. So in a way, also what you can do is you can find the effective field at that point. Okay, so if you want to find the field at point P, the force on a charge at point P, you can find the effective field at point P and then multiply by the test charge. That would give you the same value. Or what you can do is you can individually find the force of each of these pairs with the test charge, right? So that is what is being done here. So that gives you the net charge. And now if you don't have a point charge or a discrete system of charges, but rather if you have a continuous distribution, you have to go from summation to, so you have to go from summation to integration. So that's what is being done here. So if you have a charge density, line charge density, which is given as lambda, then for dl line element, your charge that comes out is lambda into dl, right? And then the distance is given as r. So it's the same formula, but now if you have to integrate over the entire line or entire line of charges or entire line element, right? And similarly, you can do it for a surface charge distribution where the surface charge density is given as sigma. It is the charge per unit area. This is the charge per unit length. And similarly, you can have charge density per charge density like volume charge density or charge per unit volume. And then this is how you can go from go to the continuous distribution of charges. So now we'll use those concepts to do some standard derivations. So suppose if you have this line charge, a line of charges. So it's a continuous distribution of charge with uniform line charge density of lambda, and the distance from this distribution is given as z. It's vertically at a distance of z from this line, and you want to find the electric field at this point P. So how do you do that, right? So what you do is now you consider an element which is given as, suppose, some element dx, okay? So the delta q charge in that element will be given as lambda into dx, right? Just in this element. And then what is the distance from point P to this element? That is given as r, right? So how do you find it? So that would be given as x squared plus z squared, right? And then now you put it in this formula. What's important to note is, see here, you have to find the components individually. So you have to find the z component and you have to find the x component. So in order to find the z component, what you can do is you can take the cos theta term here. So the electric field will be directed in this direction. So it will have two components, z and x, right? So now if you want to find the z component, you take a cos theta term, right? That is what is being done here. So 1 by 4 pi epsilon 0 lambda dx, that is for this line element, and then divided by r square, which is given as z square plus x square, and then you take the cos theta term, right? And cos theta is again given by z by r, right? And then you do an integration from 0 to L. So if you do that, what do you see? So you see that, like, if you do the entire derivation, so you would get a value like this, right? And similarly, now if you want to find the x component, what do? So now you take this component along the x direction. Okay, so you have to then take the sine theta component. So again, you take the sine theta component and you do the derivation. So what you get? You get something like this. So now this is your x component. So the net electric field will be this term into x cap plus this term into z cap, right? So in order to check, always when you are doing this kind of derivation, so it's important to check whether it's correct or not. And how do you check that? You check that by going to some limiting value. So suppose now if you consider that your z is much, much larger than L. So what do you expect? Then this entire thing should look like a point charge, right? Point charge with an effective charge of lambda into the total length, right? So what should be the field then? It should be something like 1 by 4 pi epsilon 0 lambda capital L by z square. So in the limit of z much, much greater than L, this expression should look like this, right? And if you put the values, like if you ignore, if you neglect L, and then for, okay, so if you neglect L, so what would you get? You would see that for with z much, much greater than L, the x component goes to 0. So why? Because now you are neglecting L. So 1 second, what am I saying? Am I saying it correctly? Yes. So this term remains. And so what happens is 1 by 4 pi epsilon 0 lambda L, and then you can ignore this term. So you'll have z out of the bracket, and then it should be z into z. So you're getting the same term as was expected. So as expected for a point charge of given as lambda into L. So this is how you find for any kind of distribution. So now using the same concept, how do you find the electric field at a point P, where now you have a square, okay? And there is, so along the line of or along the edges of the square, you have a line charge density of lambda, okay? And you want to find the electric field at the point P. So can you tell me how to proceed with this question? Like, depending on what we just discussed, how can we use that information to solve this?
Ma'am, can we make use of superposition, like from a side of A, we'll take the net electric field applying on P, and then we'll multiply it by 4, like the superposition we do. Is it possible?
Exactly possible. But
Okay.
one thing that you have to take into account is you cannot, so there'll be a component, right? So suppose
Yeah, yeah, ma'am.
right,
That is for sure that we have to break down the component in x and y directions, like electric field in x and z direction, I think, right? And
right. And if you look
this will
closely,
change. Yeah, yeah,
if you
yeah,
look closely, what will happen to your x components? It's symmetric, right? In the xy plane.
yeah. It is, but what when we see it in z direction, right? So
Hmm. No,
it
your
might change.
superposition will absolutely work. That's what we
Yeah.
have to do. There is no doubt about it, because otherwise so that's how this will proceed. There is no doubt about it. Now to
Okay.
simplify it further, just think of your structure, right? So initially, if you look back here, there was no symmetry in the x direction, right?
Yeah.
But in this structure, you have a symmetry, right? So
Yes.
because of that, what will happen is your sign components will all cancel out. So what would remain is the z component,
Okay.
right? So
Mhm.
you can just find the z component and then do it for all the four sides, right?
Yeah. Perfect. Yeah.
Clear, right?
Yeah. Perfect.
Yes, right. So if you do that, so what is being done is this is for just one side, okay? So for one side, what do? We use the same concept here. Obviously, the x sides cancel out because, as you can see, this has a vector. The electric field will be pointing along this direction. This electric field will be pointed along this direction. And now if you cancel, uh, so what will happen is it will have a component in this direction of x, and this will have an equal component in this direction. So those will cancel out, right? So only what will remain is the z direction. So now you find the field for one side of your square, okay? And if you do that, you do an integration from 0 to L. This is just substituting the values of cos theta and r and running the value of x from 0 to L. So if you do that, this is something that you get, okay? And again, this is just the consistency check. And you see that at a distance of, so if you have an infinite wire, you are supposed to get an expression like this, and you get a similar expression. Okay, so now you use this result for all these four edges. Okay, so for your case, now your L will be equal to a by 2, right? So and your Z will then be, so this will become Z square plus a by 2 whole square. Why? Because this distance. So it's like, uh, how do I explain? So this is a by 2, and then you also have, so this is Z. So you also have a third component, right? This a by 2 thing. So this is because of it's in the xy plane. Here it was just in the xz plane, right? Here it's x, y, and z. So you also have to consider. So when you find the net distance, it will also have this a by 2 component, right? Because of that, z becomes root over z square plus a by 2 whole square, right? So if you do that and if you put those values, this is your field of one edge, right? E1. And now you do it for four sides. So what you multiply is you multiply it by 4 cos theta because you only want to take the z components. Other component cancels out. So now this is your expression for the field. Clear, right? Clear to everyone?
Yes. Yes, ma'am.
Okay. Now suppose if you have a similar thing, but now you have a ring kind of structure. Okay, so it's a circle and it also has a line charge density of lambda, and you want to find a field at a distance z. So what do you do now? So now you have to again work with the similar concept, but then it's important to see how you take the line element, right? So what you do here is, see again here you are taking this line element as lambda dl. Suppose some line element here which is given as lambda dl. And how will your r change? Your r will change as z square plus r square, where this r is your radius of your circle or ring, right? Sorry. And if you put those values here, right, again, the horizontal components will cancel. So only the vertical components will remain. So you get something like this. But now what you have to do is you have an integration here, right? And this integration is over dl. All other terms are independent, like this cos theta term or this terms. These are all independent of your integrating factor, that is dl, right? So you can take all of them out of the integration. And if you integrate over dl, what do you get? You get the circumference of your circle, right? And that is given as 2 pi r. So you can just put that value here. So that gives you the field for this ring at this point P at a distance vertically Z above. Okay. So now the same concept, we'll try to extrapolate and try to find the field for this disk. Okay. Now it has a charge density. It has a surface charge density given as sigma, and we want to find the field at the point P at a distance Z from this disk, right? So how do we use the last concept? And so how do you use that concept to evaluate this field value? Any idea?
Ma'am, this time we might make use of area of that circle. Like we will take a small element of area A and we'll check how much field is reacting on point P, and then we'll integrate to all over the area.
So the concept is similar, like you're telling the right thing, just the way of telling is slightly, so it might be mistaken. So see, what's happening is now initially you had a ring of a fixed radius. But now what you have to do is you have to integrate over number of such rings of different radiuses, right? So your radius would value R would keep on changing, right? Is it clear? So how do you integrate over the area? What actually will you be doing is you'll take one ring element here, another ring element here. Similarly, you'll have number of ring elements and you'll do a superposition of all those ring elements, right? So in a
Yeah,
way
yeah,
you're
ma'am.
doing an
Ma'am, that is what I was trying to say. That will
okay.
ultimately the area will dependent on radius only, right? Like how much
Mhm.
radius will change, accordingly the area will also change, right? Because
Right. So
pi is a constant. Yeah.
yes, so
Yeah.
here your R was constant, but now in this question, your R won't be a constant value, right? And that's how your concept of area is coming into picture. So what we now do is, so we break it into rings of radius R and thickness dr, okay? And then we use the same expression for field of each ring. So total charge on a ring is given as sigma into 2 pi r into dr, right? 2 pi r is the circumference, dr is the thickness. So what is the total area? 2 pi r into dr. We multiply it by sigma to get the total charge, right? And that is also equal to lambda into 2 pi r, right? If you go back to your description of a ring, so in a way, your lambda is actually equal to sigma into dr. So for a ring, we just derive that this is your expression for the ring, right? Like if we go back, this is your expression for a ring of radius r with line charge density of lambda. So for this case, for one particular ring of some radius r and thickness dr, your electric field for that ring would be given by this expression here, where lambda is given as sigma into dr, okay? And this is the same expression. But now when you find it for the disk, what you do is now you integrate it over r. So your r now varies from 0 to capital R, right? So if you do this integration, you would get something like this. So this is your electric field for this disk with a uniform surface charge density of sigma, right? So again, what you can do is, suppose if you consider your R is much, much greater than Z, right? So that means it's like an infinite plane. So what would you then get? You will get it as sigma by 2 epsilon naught. This is something we had initially seen, right? If you have an infinite plane, or it might come in the coming classes as well. So, or I guess it's it's already known to us in a way, right? We know how the field changes for an infinite plane, right? It's given as sigma by 2 epsilon naught, and that's what you are getting here, right? And then if you consider that your z is much greater than r, again you can think of this as a point charge, right? With the charge given as pi capital R square into sigma. That is your total charge, and you consider that to be a point charge. So your electric field expression in that case comes out to be something like this, right? And which matches with the point charge description, right? So that means this expression is consistent. Okay. Now, can you tell me how to find the electric field at some point P from a sphere with uniform surface charge density, right? So now you have a sphere, okay? And then you want to find the field at the point P. So how do you do that? It's the same concept, same concept, like you have to consider an element here and find the distance from the test or the field point, okay, and do an integration. So can you tell me how to proceed with this? Okay, you guys can see, right? This is being recorded. I'm just worried if it is not recorded. Is it recorded? There'll be some. Yeah, I guess so. Okay. Okay, so any idea how to proceed with this now?
We can consider the disk model from the left extreme to right extreme, where the disk radius decreases with respect to the center cut piece, like
Okay,
integrating multiple disks
like
of various radius,
yes, but
or two
there's an
hemisphere
issue.
model. Yeah, okay.
Ma'am, I think we might make use of triple integral or double integral because it is also varying in z direction. The ring size is also varying in z direction.
Right. So what would happen if
Yeah.
you consider a disk, first of all, is that, see, if you have a disk of some surface charge density, then you have another disk of some surface charge density. So, are you considering a disk like this in the XZ plane, or were you considering something like XY? So if you do it in XY, then it's not correct, because then you have charge all over the sphere. But in this case, you have charge only on the surface. Now, even if you consider uh, the x the xz plane, and if you cut it into disks, it would be it might be possible, but the problem is that there are multiple integrations as pointed out. So what would happen is each of the points on the disk would have different distances from the point P, right? So your concept works if you have a disk in the xz plane, okay, and then you integrate, and you can also consider z to be varying and do something. But in this case, if you consider the disk along the xz plane, what would happen is along the disk also your position, your distances would be varying, right? So one easier way would be to just consider an element like this, okay? So some element you consider, right? So this is your element. So what is the charge in that element? So you have some surface charge density sigma, okay? And you have some element here which is given as r square sine theta d theta d phi, okay? Why don't we have dr here? Because it's on the surface. If it was a solid sphere with a volume charge density, right? In that case, you would have small r here, and you also have to integrate over the radius. But for this case, you are just on the surface of the sphere, so there is no integration over the radius, okay? So that's why what would happen is this is your element, like a single surface element that you have taken, right? And then you are multiplying it with the surface charge density. So this is your dq. And what is your distance from this point? So you find it as r square plus z square minus, so it's like, you have to take this component here. So it's like, how do I point it out? So it's like taking the how do I explain? So it's like the vector subtraction concept, right? So it's like r square plus z square minus 2r z cos theta, because you're doing a subtraction of these two vectors, right? And theta is the angle between z and capital R. Okay, so this is the vector subtraction concept. And then you know what is cos phi, right? So this is your cos phi value, which comes from the geometry of your structure. So now if you put those values here in the value for Ez, again, if you see, because of the symmetry, your x and z, x and y components are not here, right? You only have the z component, okay? And what you do here is that you put those values. So this is your dq term, okay? 1 by 4 pi epsilon 0 q by r square, okay? And then you have this is the cos phi component that you are considering. So if you put all those values, and then this is just some substitution for the integration that we are doing. So if you do those integration, and it has some, so as you can see, some partial fractions, and so it just substitution. So you have to substitute u by cos theta, then you would get something, okay? And then again, this has to be simplified. So if you do that, like simplifying it to be a perfect square, and I think there are formulas for solving this kind of integrations. So if you do that, you would get this expression, okay? And it's important because now what you see is that for z greater than r, your Ez is something like this. So what is this? This is like you're considering it to be a point charge, which is given as q equal to 4 pi r square sigma, right? So anywhere outside the square, it's similar to a point charge kind of field that you are observing, right? Where the charge is given by the total charge on the sphere. And anywhere inside the sphere, what do you get? You get the net field to be 0, right? So this is important because, so this tells you that if you have a shell with some surface charge density, the field inside is 0. And you would later see that this also comes out of Gauss's law, and other ways of finding out fields would give you similar results, okay? So this is important to remember. Okay, clear, right?
Yes.
Okay. So now let us discuss some of the questions. So these are some questions from previous year's assignments. So this question was is a very simple question. So which of the following statement is correct? So this is a very straightforward question. And what do you think the answer is? Very, very simple, right? Charges of same polarity repel each other.
All of
Correct?
above.
All of
All
them,
of them.
right? Right. So this is a very, very straightforward question, which was in the previous year's assignment. Okay. So now this is another question which says that this is your unit vector in some vector is given, and you want to find the unit vector along this direction, right? So what do you do? What is the how to do this?
What
All these
Just
are pretty
dividing it by
straightforward,
the magnitude.
right? And can you just tell me what the answer will be?
Was it B?
Yes. So this is how we do this. Very, very straightforward. Okay. This is another question which says that this is your surface charge density, right? And these are your dimensions of your plane surface. Now you want to find the total charge on the surface. So how do you do this?
Ma'am, we have the parameters of the surface, and we already know that for per meter square what is the charge density, and we'll multiply it with the whole area, and we'll get the total
Right.
charge on the surface.
Right. So what do we do is something like this, right? So it comes out to be 25 millicoulomb. So this is your answer, right? Similarly, if you have some volume charge density and some given volume, what is the total charge? Volume into the charge per unit volume, right? Okay. So now here you have some charge Q1 of 70 microcoulomb at some position, and you have another negative charge Q2 of 10 microcoulomb at some position, and you want to find the magnitude of force F2 on Q2. Okay. So how do you do it? So these are again straightforward. So it's what you can do is you can write the position vector for Q1, you can write the position vector for Q2. And so how do you find the separation vector? It's R2 minus R1, right? So this is your position vector. This is a separation vector, right? Now you can find the magnitude of the separation vector, which is actually your R, which you use in your expression for force, right? And then you know what is your force. Your force expressions, like the magnitude is given as 1 pi 4 pi epsilon 0 Q1 Q2 by R square. Okay. And you want to find the magnitude. So what you do is you evaluate these values and you get something like this. Okay. So now this is your answer. So this is also straightforward. The next question says that you want to write the force now in vector form, right? So depending on what we just did, can you tell me what would be the vector form for the force? You can use these results if you want.
Good evening, ma'am. Ma'am, will these questions of the doubt
Yes.
clearing session be provided in the course?
Question of the
The questions which you are currently doing in the doubt clearing session will be provided in the course?
I'm not sure about this. These were some questions from previous year's assignments, which we are supposed to discuss. So in your courses, in the current course, were you given some assignments or no? Not yet.
Yes, ma'am, we are given assignments and we have a deadline also.
Okay, and those questions are not the same as this, right?
They are similar.
Yes, ma'am, we have.
Yeah, they are similar, but are they identical? Because if they are identical, then I'm not supposed to discuss before the deadline. So that's why I'm asking. Hello?
Ma'am, this is similar questions, ma'am. I think.
Similar
Yeah,
questions, right? But not exactly same question, right? Because these questions, so what we were told was to discuss some of the questions from previous assignments, okay, previous year's assignments. So we have some access to some previous year assignments which we are told to discuss. So these are some previous year questions that we are discussing, but we are not supposed to discuss the current term questions before the deadline. Okay, so I guess they are not exactly identical, right?
No, ma'am, it is, I think it is identical one, no.
It's identical.
Yeah.
Oh God.
Okay.
Okay,
Yes.
Please.
and when is your
Ninth, ma'am.
okay? When is the deadline? Is okay because we were said that we can discuss the last year's questions. So that's why I was just discussing. So in that case, it's not a good idea. Okay, so
Anyway, you please clear it with other people also.
No,
Actually,
so
first
I just
assignment we already posted, but it is a similar questions, and the one more request is we need a different type of question, because last time itself I attended the examination and course, but I failed to pass in the last uh, semester. So if you give some other different types of problems, or then we can manage it for final examinations, ma'am, because the examinations was different. We could not make
see, ma'am,
actually.
no, I
Mm.
understood. The problem
Ah.
is, see, I have no idea about what kind of questions you like the instructor would be giving for the examinations. Okay, so basically this is something like we the PMRF fellows, we are supposed to clear your doubts regard do some this kind of sessions where we are told that in this week this is kind of questions that you can discuss, or these are the topics that you can discuss, and you can clear your doubts, right? So that's what we are supposed to do, but we actually have no idea about what questions your instructor might give in your exam. So
Yes,
in
madam.
that way, yeah, so what I can suggest is, if you have some particular questions, right, so you can ask me the questions, and I can try to solve it out in the next session or something like that, right? So if you solve some questions and you get stuck, you can ask me in the live sessions, and I would try to solve them in the next session. That I can try to do. Okay. And if I find some standard questions, I would see, I would try to share some standard questions, or but I actually have no idea about what is the standard of examination or type of questions they might give in the exam.
It is different, ma'am. That's why I asked you to share or discuss with that type of questions. Because
right, but okay.
That's why I'm
Okay.
asking, because this type of this one now you have taken that sphere and the straight line, that and all okay, but the questions were asked in the last semester was different, and we could not make it. That's why I'm this time also I'm registering, and I need that type of questions. Or I want to know what type of how can we prepare for
so
that.
the thing is, how do I access the last year's exam questions? I don't have access to last year's exam question.
Even we don't know how we don't have that I access that type of questions, ma'am. Even I don't remember what type of questions they asked.
Okay.
Okay. That's
No,
why
if you could tell me, like if you could in a way tell me what type of questions were asked in the last exam, I would have understood what is the standard, right? Right. Hello.
Ma'am, up to question number 4, I think whatever assignment question we have given, up to question number 4, I think it is identical. Question number 5 onward, I think it should be similar, not identical. It should continue, ma'am.
No, that's the issue. Point is, I might be, end up in trouble. So the thing is that we
no,
were
up to
told
4,
that.
it's
ma'am, that I fifth question I don't see now. What he told, maybe it is not
yes,
identical.
ma'am, you should continue, ma'am. You should continue. You started, you continue.
Yes,
with
ma'am, you
trouble.
should continue, ma'am.
You
No,
went
no,
up
it's
with trouble, please, ma'am.
No, I understand. It would be also be helpful for you guys, but the
yes, ma'am.
issue
Yes, ma'am. It's
here,
very helpful.
I understand. I can understand your situation, but the point is, we are categorically told that we are not supposed to discuss questions of current session, right? So if in a way, because this will everything will be checked, okay? So if now this
But
comes
ma'am,
out to
next
be
week
that.
onward, we should provide the numerical type based question. This would be very difficult for us. But this week is only for MCQ question. If you provide the answer, it would be very helpful.
Yeah, but yeah, so I can rather tell you about how to solve the questions, but I cannot tell you the answers. Okay. So that
Okay,
it's
ma'am.
better you try to solve it yourself. But because I thought that the questions would be different because we were said that we can share the last year's questions, but now it seems that the questions are same.
Maybe
So
different, ma'am. We didn't see the question
now
number
that's
5,
the
6,
problem.
7.
Even I don't know the present question assignment questions, right? So that's the issue. It's okay. So see, suppose now for and regarding the previous like the exam questions that you were telling. So if you can just see, because I don't have access to the question papers or the examination questions in the previous sessions. Okay. So if you tell me about what type of questions would be better, like, uh, better to discuss, or what is the standard of questions, or where you are getting stuck, then I can try to include them in my classes. Okay, but otherwise I also don't know what questions they're asking in the examination. I am just having access to some assignment questions and the topics. Okay, so if you have some particular doubts, you can tell me which portions or which questions, which type of questions you are getting stuck. I can try to include them in the
Excuse me, ma'am.
classes. Yes.
Ma'am, can we share our doubts with you in any particular group that you have made, or it is here and here only where we can share it with you?
So
Like,
it's
is
better
there
if
any?
you and I think there's some, like, you have some discussion forums, but
Yeah.
the better thing would be if you jot down your doubts and if you share it in the chat box during the classes. I would have access to that, so I'll keep that noted, and then I'll discuss it in the next class or the upcoming classes. So that would be best.
Okay, ma'am.
Right. Okay, so now for any question, suppose if you want to find the vector form of some force, okay? So how do you do that, right? So if you have to do that, you now know the magnitude. So you know how to find the magnitude, right? Your magnitude value would be 1 by 4 pi epsilon 0 q1 q2 by r square. So if you know the separation vector, if you know the magnitude of the separation vector, okay? And then if you so here, as you can see, you had a minus sign which you did not consider, right? So when you're finding magnitude, you don't have to consider all that. So you can just find the value. So that is your magnitude of force. But then when you want to find the vector form, what you have to do is you have to use the vector form of r. Okay, so along with this magnitude, or so if you consider this value, so if you write it in the vector form, how will this be? So then you are not considering the magnitude. Okay, you're considering the total force in the vector form. So how do you write it? You write it as 1 by 4 pi epsilon 0 q1 q2 by r square into r cap, right? So what is r cap? R cap is the unit vector along r12, right? So now you know this is your r12. You know this is your magnitude. So if you divide by the magnitude, you would get the unit vector along this particular direction. And then if you multiply the unit vector with this expression, so that gives you the total vector representation of the field, right? So the moment you consider the unit vector along the position or along the r, that is the separation vector, that is how you are bringing in picture the direction of your force, right? And that gives you the vector representation. So now you know the magnitude, and what you do is along with that you write an r cap term, right? And the r cap is given as, one second, okay, and r cap is given as r12 divided by its magnitude, okay? And that would give you the net vector representation. Okay. Now, I won't discuss the other upcoming questions. It's not a good idea. But what I'll do is I'll give you an idea about how to solve. If the questions are similar or if the questions are identical, you would have some idea how to solve it. Okay. So now if I go back, see, okay, so now this is your, this is how you had defined all of your components in the different directions, right? I had discussed about the curvilinear coordinates, and you saw that this is how you can define the components along U2, U1, and U3, right? This part was clear, right? This is how you were writing your arc element or arc length. Now, suppose if you are asked to find the area, okay, how do you find the area? So if you find, suppose if you first consider your rectangular coordinate system, right? So in rectangular coordinate system, how will you define the vector, area vector? So what is the normal to some area? That is the direction of your area, right? So what you say is, suppose you are in the xy plane, so you write it as dx dy, that is your area in the xy plane, and the direction of your area element will be along z, right? Similarly, if you are in the xz plane, your direction of your area vector will be along y, and if you are in the yz plane, your direction of area vector will be along x, right? So how are you getting that? You are doing a square, a cross product kind of thing, right? So what you have to do here in that case is you have to do a cross product between these terms, right? So if suppose if you consider any curvilinear coordinate system, what will you do is, for the first area element, how do you find the first area element? Okay, so that is what is the area element along E1 direction, maybe. Okay, so how do you do that? That would be E2 cross E3, right? E2 cross E3 would be along E1. So the value will be H2 du2 plus H3 du3, right? And you know what is your H2. So for cylindrical coordinates, you know what is your H rho, what is your H5, what is your Hz, right? So depending on these values, now if you put those values here in your expressions and multiply this term with this term, again, like pairwise, if you multiply, that would give you the individual area elements along the different directions, right? So there could be some questions on area elements, and that is how you have to solve those questions, okay? And then for volume, how are you doing the volume? So you see, similar thing. So when you're doing the volume, you're multiplying it. It's a scalar triple product, A dot B cross C, something like that, right? So similarly for area, what will you do is you will do E1 cross E2 term, then E2 cross E3 term, and E3 cross E1 term. So terms like that, right? And each of those coefficients in the beginning would be your different area elements, okay? So that's how you find area elements in different curvilinear coordinates. Okay. And this question in particular, if you look at this questions, this question is similar to some questions in your assignments. So if suppose if you have a vector where there are all constants here, okay? So what would change in that case, right? See, you are doing the same case. You are given some vector in the rectangular coordinate system. You want to change from rectangular to cylindrical coordinate system, right? So for any kind of vector, this is how the process will be, okay? But now, suppose if you have some constants here, so that makes your work simpler. Then you don't have to replace this z, x, and y by these values, because constants are same in all coordinate systems. So there you just have to replace your I cap, j cap, and k cap by the corresponding expressions in that particular coordinate system, right? And if you do that, you would get the expression for the components in that frame, right? And if you have, suppose that's for a constant. Again, if you have some values here, like some xy values, then do the substitution of xyz based on how you are defining xyz in terms of your new coordinates. Like in the spherical coordinates, you know that this is how you will be defining, right? So in the spherical coordinate system, if you have x, y, and z, you have to, so if you want to change from rectangular to spherical, you have to change x, y, and z by these terms. And you have to also write I cap, J cap, and K cap in terms of R cap, phi cap, and theta cap, right? And if you want to go from rectangular to cylindrical, you have to replace X, Y, and Z by these expressions. And you have to replace I cap, J cap, and K cap by rho cap, phi cap, and Z cap. So that's how this is supposed to be done. If there are constants, you don't have the same in all coordinate systems. So I guess to the later questions, this is how this all questions are based on the same concepts. So whatever questions if the questions are similar or identical, I guess this concepts would be sufficient to address those questions. Okay. Any doubts in this section? Okay. So if not, then I consider that these things are clear, right? So I won't be discussing anything further today. So if you have some doubts, you can ask me now.
Ma'am, electrostatic force is considered to be more powerful than the gravitational force. So other than this, going through the formula, which is kq1 q2 by r squared, like because the distance between the subatomic particles is small, so the force is powerful. And in the case of gravitational force, the distance between the celestial bodies is much more, so the force is considered to be a bit less. What can be the other possible reasons?
So see, both of them are both of these forces are long range. So it's not just the distance, it's also the magnitude of. So suppose if you talk about gravitational forces, it's given as you have this product of m1 m2, right? So for that to be significant, obviously the distance is a factor. So if they are too large, but even suppose if you have two small balls, right, and they have some mass, and you hold them together, they won't get attracted, right? So it's also because it's not just the how do I express? So it's not just the distance that makes the difference. It's also so your so why is it relevant for the celestial bodies is also because their masses are huge. Okay, so it's so the gravitational constant, and here if you have this 1 by 4 pi epsilon 0, this term, what is the constant? How is the constant uh, overpowering in which mass ranges? So in our normal realms, like in the things that we deal with, the masses are not that strong enough to result in forces like such kind of attractive forces. So you need huge amount of masses to result in such kind of like significant attraction or repulsion, like attraction, obviously attractive gravitational forces. Okay. While here, what happens is obviously this distance is like the distance between the interparticle distance for electron proton. You can consider that the distances are smaller, so they are getting attracted. But that's not all. That's not the only consideration here. It's also the realm in which they are. So that see if you consider how do I express? So like here. So when you have two charges, when you rub your comb and you have some electrostatic charge developed there, it gets attracted, right? So why is it happening at that length scale? If you have two balls at the same distance, and like if you keep them close enough, okay, and then you have a comb with some charge, okay, and then you bring some papers close to it. So the distances are similar in both the cases. But in one case, you will be able to see some kind of a force. In another case, you won't be able to see it. So it's not just the distance. It's also the masses, and here the charges that are developed, and also you have to consider the value of the gravitational constant and this 9 into 10 to the power 9 factor that you have in case of electrostatic or electromagnetic forces.
Okay, thank you, ma'am. And ma'am, one thing more, that is the value of the G was said to be determined with the help of K and the experiment was the torsional pendulum. So why was it used?
Why was it used? This I have no idea. I might try to look it up, but I have no idea why particularly that was used. Because see, normal simple pendulum, like these are some experiments also that we generally do in lab even today. So we do a pendulum experiment. Even I have done in my in my lab days. So I have done this 2 pi root over L by G, and so it's just a one particular way of getting the value of G. But I actually don't know why exactly that was chosen and why not something else. So I might try to look it up, but for now I don't have an answer to this.
K was used, like why the concept of K was used. Is it because that the subatomic particles are also rotating and the celestial bodies are also rotating? So is it that the reason?
Yeah, I have no idea, but I don't think that might be a reason. The reason might be so the reason might not be at the heart of whether the subatomic particles are rotating or not, but I need to look it up in order to answer these questions properly. But that might not be the sole reason. There can be very simpler explanations, like that is kind of a simple manifestation of gravitational uh, field that is gravitational force that is seen in nature. So it's just a simple manifestation which can be quantitatively measured, something like that. But I can look it up and see the history as to why this thing was taken up. But I don't have an exact answer to this now.
Okay, sure.
Okay. Any other question? So this section, this curvilinear coordinate section, you can look it up in this book called this Vector Algebra by Swarm series. Okay, this is a very good book. It has a lot of questions and this kind of all these explanations that I have taken for the curvilinear coordinates is from this book. This section is taken from that book. So that is a very good book. So you can refer to that book for this kind of vector algebra or curvilinear coordinate concepts. Okay. If there are no other questions, any questions? Okay, so if not, let us call it a day. Okay, so Shayali, you have some question? Okay. Okay, so I'll stop the recording, and if you have some doubts, you can ask me, like even in the coming classes, if you have some doubts, you can write in the chat box, and I can note it down. I can discuss it there then and there, or I can also note it down and see if I can help you with that in the upcoming class. Okay, so that's it for today. Okay, so I'll stop the recording. So thank you everyone.